Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 30, part 2, or part B. We're still talking about the exponential distribution. Last time we introduced the exponential distribution. We also introduced its moment generating function, actually derived that quickly. We did not get to the mean and variance. We'll start with that in this section. So let's get started, continuing with the exponential distribution. And last time we left off with the moment generating function, which is given here. And remember, those are unique for each distribution function. So to get the mean, we're going to take the derivative and make sure that you use your chain rule. So we take -1 out to the front, we have this, we subtract 1 from the exponent, and then we take the derivative of what's inside the function, or parentheses in this case, which is going to give us a negative theta, which cancels out the negative in the front. And don't forget to write that t is less than 1 over theta. But what we're going to do here is we're going to plug in for the mean. We're going to plug in 0, which is definitely less than 1 over theta. And that gives us mu equal to theta. So the mean is equal to theta. So this is similar to the Poisson distribution, whose mean was equal to lambda, if you remember. But unfortunately, we don't get the same value for the variance, so it's not quite so easy, but it's very close. So we're going to take the second derivative of the moment generating function. Now we have to use the addition rule. I did this negative exponent here so that I wouldn't have to use the product, the quotient rule. I could just use the product rule, not multiplication rule, the product rule. So again, we've done that, and we come out with this expression here. There's not a lot of reason to try to simplify too much because we're plugging in 0 for t, but again, to be proper, make sure that you list your limit for t. And the second derivative at 0 is ex squared, which is 2 theta squared. So remember, the variance, var x, is ex squared minus ex quantity squared. So ex squared, we just said, was 2 theta squared. And then ex is theta, so squared is theta squared. So 2 minus 1 is 1 theta squared. So sigma squared is theta squared. So very handy. And of course, sigma will be equal to theta. So just be careful to write that down for your distribution and don't get it mixed up with the Poisson, whose variance is also lambda and the mean is lambda. Here we have the mean is theta, but the variance is theta squared. Okay. So the index of skewness is given by this expression. And if you remember, the third moment, centered moment on the top. And it turns out that this is actually 2. And so it doesn't matter what theta is. It does not depend on theta. This is positive skewed. In fact, the exponential distribution looks like this. Okay, so it intersects the y-axis at 1 over theta, and then it continually decreases. This is what we call this is a skewed distribution, and we consider this kind of an extreme distribution. A lot of times we'll use this distribution and see if some new theory works for it, some practice works well for it, and if it does, then it's very likely that it'll work for many other distributions, if not all of them. So let's take an example here, and let's look at how a problem could be written. Customers arrive in a certain shop according to an approximate Poisson process at a mean rate of 20 per hour. So question A, what is the probability that the shopkeeper will have to wait more than 5 minutes, notice we're in time, for the arrival of the first customer? That's telling us that this is going to be an exponential distribution, exp theta. So theta is going to be 1 over lambda. Now, but we say 5 minutes, more than 5 minutes, so our unit's going to be in minutes. So let x be the waiting time in minutes until the first customer, And so lambda is 20 per hour. So how we convert units is 20 per hour means 1 hour divided by. And so I want to cancel out the hour, so I can multiply by a fraction with 1 hour on the top, and that will cancel with the 1 hour on the bottom. And then 1 hour is equal to 60 minutes, so I put 60 minutes on the bottom. 20 over 60 is 1/3, so this is 1/3 per minute. Make sure you do not try to change this to decimal, or you might end up with the wrong theta, because 1 over 1/3 is exactly 3. So if you're rounding this to decimals, you're going to get a little off on your theta, and there's no reason to be off. It's exactly 3 minutes, okay? So please be careful. That's another reason that I've been emphasizing to leave things as fractions many times. This is another one of those times. So we're going to invert the fraction. So theta is 3 minutes. Lambda was 1/3 per minute. That's divided by minutes. We invert that. We flip it over. The minutes go to the top. Okay? So we can write our PDF. Make sure that you do that. For all the problems, write out the PDF. I'm going to ask you to do it on the test. You need to get in the habit. So I like to write out the formula first. So 1 over theta e to the negative theta x over theta. And I wrote this wrong. So this is x over theta. Okay. And so this is 1 over 3, because theta is 3, e to the negative x over 3. Okay. So this is what I'm looking for when I ask for the PDF. The values actually put in. If there's any that can be reduced, like if it's subtracting or doing something, then of numbers, then do that. Okay? So always write the PDF. Then it says more than 5 minutes. That's what we want. We want more than 5 minutes. That's greater than 5 minutes. So we can write the probability that x is greater than 5 minutes, and that is an integral from 5 to infinity of, here's our PDF, and I forgot dx. So make sure you remember your dx there. And so when I do this, the exponent here, I'm going to divide by that. So that's 1 over negative 1/3. And so the 3 on the bottom cancels with the 1/3 on the bottom, and I end up with a negative. And so I still have the negative here, so I don't know what I was doing there. And it's e to the negative x over 3, 5 to infinity. When I plug in infinity, or approach plugging in infinity, this is e to the negative infinity. That's 1 over e to the infinity divided by 3. That is equal to 0. So the minus sign is not going to have an effect there. 0 doesn't have a sign. And then I'm going to subtract when I plug in this, but I've got the minus sign, so subtracting a negative is adding. So that becomes positive. I plug in 5 for x. I get this value here. Okay? And you can work that out. I suggest that even though I'm happy with this answer, that you verify that you haven't made a mistake. This number has to be between 0 and 1. And so second e to the negative 5 divided by 3 gives me 0.18875. Okay, so 0.1889 would be to 4 decimal places. All right, and sometimes we like the decimal places, but I want to see that you know the exact answer as well. Okay, so let's go ahead and try to find, let's see, the median here. And so that is, I'm going to zoom in a little bit so we can see, that is pi sub 0.50. So because the median is where half of the probability is below and half is above. Okay, so we set 0.5, the subscript here, that gets set equal to the integral from the lower limit up to here. Now, the exponential, you've seen the graph, it's a continuous distribution. There's no steps or pieces to it. So we're safe to just integrate. If you have a piecewise or stepwise function, you have to be very careful to look at the graph of that PDF and make sure that you understand about where the median or whatever percentile you're looking for is, because you may have several integrals that you have to work through to get to the answer, and you need to be looking at those pieces of the function. Okay, so this is going to be general terms here, 0 to pi sub 0.5 f of x dx. Now I'm going to substitute in for f of x. We have 1/3 e to the negative x over 3. And I take the integral, and the 1/3 here cancels with the 1/3 here. It's still negative, but it's left here negative e to the negative x to the 3. So I can plug in pi to the 0.5 sub 0.5. And when I do that, I get negative e to the negative pi sub 0.5 over 3. And then I subtract from a negative, and that's a positive. And then I plug in 0 for x. E to the 0 is 1. So I can rewrite that as 1 minus e to the negative pi sub 0.5 divided by 3. And that's equal to 1/2. You could leave it as 0.5. You're going to see where this might be handy to leave as a half, because I'm going to take the natural log of both sides, and when I do, I'm left with the exponent on this side, and ln of 1/2. If you remember your properties of logs, ln of 1/2, a fraction, is equal to ln of 1 minus ln of 2. And ln of 1 is 0, because this is log base e, 1 equals y. E to the y equals 1 only if y is equal to 0. Okay, so I can always remember that log 1 is 0. And so this leaves us negative log 2, and we have is equal to negative pi sub 0.5 divided by 3. We solve for that, and we get 3 ln 2. If you want to know what that's equal to, 3 times natural log of 2, 2.0794, etc. So that's approximately what the value of x, remember this is a value of x, the median is going to be around 2.08 there. Okay, so that's where we'll stop for this video. I hope that's helped you understand how to use the exponential distribution, help you avoid some of the pitfalls that I see students have with that distribution. So make sure that you update your list of distributions if you have anything you wanted to add to that. If you have any questions, come to virtual office hours. If you can't do that, email me, but just make sure you send me a picture of the problem and a picture of your work, and I will be happy to help you by email. Take care of yourself, stay safe. We'll see you next time.